Hi students, good morning to all. Welcome to today's class on theories of reaction rate. In the previous class, we explained the one theory, that is the earliest theory, first theory, the collision theory. But the collision theory has some limitations as it does not obey or applicable to the complex reactions and reactions in solutions. And it is only explain the reactions of the simple gaseous reactions. But today we are going to learn about the most acceptable theory, that is known as the activated complex theory or transition state theory, or also known as the absolute reaction rate theory. But it is commonly known as the activated complex theory. Okay, it is developed by Airing, Polanyi, and Evans in 1935. It is mostly accepted because it can explain many types of reactions, including reactions in solutions and reactions in gaseous state, etc. So it is commonly accepted one. Then, according to the activated complex theory, the reactants are first converted into a high energy molecular species that is known as the activated complex. That is, before going to the product, the reactant molecules combine to form a high energy molecular species. This high energy molecular species is known as the activated complex. This this activated complex is as it is high energy, so it is unstable, and it is converted into product, or it may be come back to the reactant. It depends on the energy difference. So then the next is the activated complex is converted into product. Here, consider the reaction in which the two reactants A and B react together to give the product. In the first step, the A plus B, A and B combine together to form an activated complex. This represents the activated complex. So it is a reversible reaction because there is a chance for or probability for converting the activated complex into the reactants itself before going to the product. So then, or it is the activated complex is converted into product. Okay. In this activated complex, it is a high energy species, and so the importance or the characteristic of activated complex is that one vibrational degrees of freedom changed to a translation degrees of freedom. That is, the one of the vibrational degrees of freedom of the reactant is converted into a translation degree of freedom in the activated complex. This represents the energy profile diagram of the reaction. It is the x-axis. It represents the reaction coordinate. Reaction coordinate means it is indicate the progress of the reaction. That is what happens when the reactant is converted into product. But it is the course of the reaction. That is what happens to the bonds or bond length, where the bond is breaking, where the bond is formed. It is indicated by the reaction coordinate, and it is indicates the y-axis indicates the energy changes that occurred for the reactants during the reaction. Okay. So it represents the energy of the reactant, and it is the energy of the product. This is an exothermic process because the reactant has a high energy and the product has a minimum energy. So it is an exothermic process. Okay. So in this energy difference, this represents the highest peak of this curve indicates that the energy of the activated complex. That is, this energy represents the energy of the activated complex. So the energy difference between the reactant and the activated complex is known as the activation energy. That is, the energy required to activate the reactant into activated complex is known as the activation energy. And then the energy difference between the reactant and the product is known as the energy of the reaction. That is the delta H of the reaction. Okay. Then thermodynamic formulation to derive the rate equation for the reaction based on the activated complex theory. Then consider the above reaction, A plus B giving the activated complex, and then it is converted into product. Then K star indicates the equilibrium constant of the reaction for converting the reactants into the activated complex because it is an equilibrium reaction. And then K2 is the rate constant of the reaction, that is the rate constant of the rate of the reaction depends on the concentration of the activated complex. Okay, that is how much reactant is converted into activated complex or how much of the formed activated complex is converted into product. That is because there is a chance for converting this activated complex into the reactant. So it depends on the concentration of the activated complex. That is the rate of the reaction depends on the concentration of the activated complex. So that is as already mentioned, in the activated complex, one of the vibrational degrees of freedom is changed to the translational degree of freedom. That is the frequency of vibration. Vibration has some frequency. That is the frequency of vibration is a measure of the rate of the measure of the rate constant. So the frequency of the vibration, that is how fast it vibrates, and then that much fast it is converted into a translated degree of freedom, that is it is converted into an activated complex. So this frequency vibration is equal to the rate constant K2 of the reaction. Then according to classical mechanics, the vibration energy is given by RT by Na, where R is the familiar universal gas constant, Na is also familiar, that is the Avogadro number, and Kb is the Boltzmann constant. So vibration energy is equal to kBt according to the classical mechanics, but according to the quantum mechanics, the vibration energy is given by h nu. Then equating these two equations, h nu is equal to kBt, then nu, the vibrational frequency is equal to kBt by h. That is give the equation number 1. Okay. Then the rate of the reaction. The rate of the reaction, that is the decrease in the concentration of the one of the reactant with the time, is equal to K2 in the concentration of the activated complex. That means K2 is a rate constant and this is the concentration of the activated complex. That is K is known as the transmission coefficient. That is the probability, it is the probability of converting the activated complex into product without coming back to the reactant. Is the probability of converting the AB star to the product without coming back to the reactant. That is indicated by the transmission coefficient. That is K2 into AB star. We know that K2 is a measure of the frequency of vibration. So K nu into AB star. We know the value, the equation for nu as the KBT by H. Then substitute the value of KB, that is first equation in this. So we can get KBT by H into concentration of AB star. So we know that it is the activated complex, it is high energy species. As it is formed, it is converted into either into product or into the reactant. So it is not easy to determine the concentration of the AB star. So we have to express the concentration of AB star in terms of the concentration of the reactants A and B. Okay. So it is known to us because we take the constant A and B with a certain concentration. So we have to express this concentration of this AB activated complex into the concentration of, in terms of the concentration of the reactants A and B, and then assuming that, okay, then the equilibrium constant K star is equal to, from this first equation, K star is equal to AB star divided by A into B. Then the concentration of AB star is equal to K into concentration of A into B. You know the equilibrium constant, how to calculate the equilibrium constant. Equilibrium constant is the product, concentration of product divided by concentration of the reactant. Okay. So concentration of activated complex is equal to K star into AB. This gives the equation 3. It is not here. So just not bothered about the type equation here. Okay. Substituting the equation 3 into and assuming K is equal to 1, that is this K is equal, that is probability, just the maximum probability of converting the activated complex into product without converting it back to the reactant, that is K is equal to 1. The maximum probability is equal to 1. That's saying K is equal to 1 and the rate is equal to K2 into AB star is equal to KBT by H. Then substituting the value for AB star, K star A into B. Okay. Then K2 is equal to, then what is the value of K2? K2 is equal to, it is a constant. So all these are constant, K constant, temperature at a particular temperature. And then we know that here K2 is equal to KBT into K star divided by H. Okay, we know that. Then from the thermodynamics, we know that the free energy is related to the equilibrium constant as delta G0 is equal to minus RT ln K. Here G0 is for the activated complex, so we can put a star in all this. So delta G0 star is equal to minus RT ln K star. We know that from the well-known Gibbs-Selmons equation, we know that delta G0 is equal to delta H0 minus T delta S. So delta G0 is equal to minus RT ln K star is equal to delta H0 star minus T delta S0 star. That is K is equal to, K star is equal to e raised to minus delta G0 star divided by RT, that is equal to e raised to delta S0 star by R into e raised to minus delta H0 star by R. By substituting this for delta G0, we can get this. Okay, here delta G0 star is the standard Gibbs free energy of activation. Delta H0 star is the standard enthalpy of activation. Delta S0 is the standard entropy of activation. Okay, then substituting this equation 5 in equation 4, that is K2 is equal to, we know that K2 is equal to KBT by H into K star. For K star, we can substitute this value delta is e raised to delta S0 star divided by R into e raised to minus delta H0 star divided by RT. This is known as the well-known Eyring equation. Okay. Then take the logarithm of this equation. Ln K2 is equal to Ln Kb by H. Here T is the variable, but these two are constant. So I separate the term Ln Kb by H plus Ln T plus Ln. The Ln of this exponential is equal to Ln S0 star by R minus H0 star divided by RT. Okay. Then differentiating this equation with respect to temperature, d ln K2 divided by dt is equal to 1 by t. That is, the differential of this constant is equal to 0 and differential of ln t is equal to 1 by t. Okay. Then differential of this is also a constant. It does not contain any temperature term, so it is also is equal to a constant. Is equal to 0. Then the differential of delta is 0 by RT, that is 1 by t. Differential of 1 by t is equal to 1 by t square. So d by dt of ln K2 is equal to 1 by t plus delta H0 star divided by RT square. That is equal to, we taking the RT square as the LCM, and we can get a delta H0 star divided plus RT divided by RT square. This gives equation number 7. Okay, that is del d by dt of ln K2. That is, we know that the Arrhenius equation that is equal to K2 is equal to A into e raised to minus EA by RT. Okay. From this Arrhenius equation, d by dt ln K2 is equal to EA by RT square. That is, taking logarithm of the Arrhenius equation and then differentiating with the temperature, it is equal to EA by RT square. It is already done in previous classes. So d by dt of ln K2 is equal to EA by RT square. Then comparing the equation 7 and 8, EA is equal to d by dt of ln K2 is equal to EA by RT square. Okay, so EA is equal to, these two are common, RT square is common, so EA, the numerator EA is equal to delta H0 star plus RT. That is, activation energy is equal to delta H0 star plus RT. Then also from the collision theory, it is explained in the previous class, that is K2 is equal to PA2 e raised to minus EA by RT. That is from equation 6 and 7. PA e raised to minus EA by RT is equal to KBT by H e raised to delta S0 star divided by R into e raised to minus delta H0 star divided by RT. If EA is almost equal to delta H0 star, we know that EA is equal to delta H0 plus RT. Here, suppose EA is equal to delta H0 star plus star, that is RT is very small compared to delta H0. So that is in that cases EA is approximately equal to delta H0 star. And then this equation 11 becomes PA into e raised to minus EA by RT is equal to KBT by H e raised to delta S0 star by R into e raised to, for delta S0 star we can substitute it for delta EA, e raised to minus EA by RT. That is, these two terms are equal, and that is PA is equal. PA is the probability factor, the orientation factor or probability factor. A is the Arrhenius pre-exponential factor, that is the product of this P and A is equal to KBT by H e raised to delta is 0 star by R. Okay. This is the thermodynamic derivation of the activated complex theory. That is, from this activated complex theory, we have to calculate the activation energy and Arrhenius pre-exponential factor and the probability factor, etc., from the known values of the thermodynamic functions like delta S, delta H, and delta G. Okay, at a particular temperature. So it is a well-known theory, and it is also explained all the almost all reactions, including reactions in solids, reactions in liquids, etc. So it is the thermodynamic formulation of the activated complex theory. So even though the application of activated complex theory to the reaction in the solution is complicated due to the involvement of solvent molecules in the activated complex, that is, in the reactions in solutions include the reactant molecules, and in addition to the reactant molecule, there are many solvent molecules. That is, large number of solvent molecules are there in the solution reactions. So these solvent molecules are also incorporated in the formation of the or in the activated complex. So this mechanism is somewhat complicated, or the activated complexes are somewhat complicated compared to the gaseous reaction, because there is no solvent molecules in the gaseous reactions. So the activated complex formation is very difficult, and it is complex one, even though the iron equation called for the reactions in solutions too. But that is, this iron equation is applicable in the reactions of reactions in solutions too. So this is the peculiarity of the activated complex theory compared to the collision theory. Okay. So this is about the activated complex theory. So stop here. Thank you. Thank you for watching.